The Origins podcast is now a part of the Origins Project Foundation. Please consider supporting the podcast and the foundation by going to www.originsprojectfoundation.org.
Hello, and welcome to the Origins podcast. I'm your host, Lawrence Krauss. In this episode, I got to have an incredibly exciting and interesting conversation with one of my favorite scientists, Dr. Andrea Ghez. For over 20 years, she and her colleagues spearheaded new technologies that allowed her to look and peer with telescopes deep into the center of our galaxy to discern the existence of a supermassive black hole. And for that work, she was awarded part of the Nobel Prize in Physics in 2020. She and I were able to connect together by Zoom in December, shortly after she actually officially received the presentation of the prize, which because of the pandemic wasn't done in Stockholm, but was actually done, it turns out, in a friend's backyard in Los Angeles. And it's a wonderful conversation because she's not only incredibly affable, but it's clear that Andrea is a scientist that is interested first and foremost in the science and is equally interested in explaining the science. And also, actually, for viewers, I think you'll find it enjoyable because she and I got to work through some concepts that we hadn't yet really thought about how to explain, and you can see the give and take as we came up with the correct explanation. Altogether, I think it was one of the most fascinating scientific episodes that we've recorded, and I'm sure you'll enjoy it. So with no further ado, Dr. Andrea Ghez. Andrea, thank you so much for coming on the program. I know it's a busy time for you, but it's great to see you again. It really is.
Oh, it's my pleasure, Lawrence.
And I have to say, I was telling you before, but I'll tell you again that I was watching the Nobel acceptance of the awards in different places around the world because of the pandemic. And yours was a favorite. You had such a wonderful smile. You were so happy. And it looked like it was in your garden. Was it in your garden?
No, it wasn't. It was in a friend's backyard. I wish I had that backyard. But...
Yeah, it was a beautiful backyard. I was saying, and was that your family around? I loved that. I loved the applause. Was that your family? Oh, that was
my two boys, yeah.
Oh, that's great. Oh, that's really wonderful. Oh, well, anyway, it was just so warm and real and genuine. And I'm just so happy for you. I've been a big fan of your work for a long time, as you know, and it's just so deserved and just wonderful. It really made my day. Anyway.
Thanks.
Okay. Now, I don't want to talk about the Nobel now. We might talk about it later. I want to talk about other things. And this is an Origins podcast. And normally I begin with talking about origins. And I want to begin with your origins, which are interesting to me. You were born in New York, right? Like me, I think. Mm-hmm. Okay. Your father came from a Jewish background, your mother a Catholic background. Is that right? Which, by the way, is the same as my daughter. I came from a Jewish background. My ex-wife came from a Catholic background. But did religion play any role in your life when you were younger?
Well, they each respected their own religion, and I think they agreed that they wouldn't force their religion on the kids. So, Good. In a sense, I think we all grew up agnostic.
Yeah, no,
but really appreciating, I think, the concept that there's different points of view and different ways that I think that it's one of the wonderful thing about having parents that come from different communities.
Exactly, I think it's really important it's a wonderful thing for kids to be able to see different communities, different points of view. And I do think, if you see two different religions among your parents, then you kind of realize, well, maybe one isn't necessarily the absolute truth. And what we did with my daughter, we just celebrated every holiday that had parties, and God didn't enter into it, but we did Christmas and Hanukkah and all that stuff. So, anyway,
the best of both worlds.
Okay, so you grew up agnostic, okay, but and you were interested in science very early. I was reading that the moon landings inspired you, and then I know you're younger than me, and I looked it up, and I thought you were somewhere between like 4 and 7 or something.
Yes, I was very young, so I think one should be careful with our, the narrative of how we got interested in science. So I think that's the point that I can point to, where I started thinking about the scale of the universe and got really interested in it. But I was certainly interested in a lot of different things.
You were extremely young, but therefore you obviously were interested in science very young. You said your mother encouraged you to do this?
Oh, both my parents were huge encouragers, I guess, of my interest. Really starting with an interest in math. I mean, to me, actually both math and science, I think, was a language that made a lot of sense to me. I was a kid who really liked puzzles. So you give me any kind of puzzle, a jigsaw puzzle, crossword puzzle, just the idea of a logic really resonated very well. And so they really both were incredibly encouraging. My dad used to buy me books, biographies of women scientists. So, in fact, I remember very clearly when I was young reading biographies on Marie Curie and other frontier women, I guess is how I would put it.
Oh, that's nice.
Yeah.
And I can't help but say, of course, and now you followed in her footsteps, as you probably thought moments after learning about it. That's a wonderful thing to have that connection, I think.
Well, I think it's such a reminder of the importance of role models.
Yeah, for me, when I try and trace my own interest in science, it was a book. The first time I can remember it really was a book I read in public school on Galileo. And for me, it was the fascination. It was the excitement of learning about the world, but also for me, the rebel, the standing up against power, all of that just seems so brave that it made science. It gave me a role model for scientists, which maybe I don't still have, but scientists sort of fighting for truth against the world, that kind of thing. And it was really, your parents both were educated. My parents didn't finish high school, but your parents, neither of them were scientists though, right?
So my dad was an economist, a professor. So he did the whole education system through a PhD. My mom didn't go to college. So my mom went to a 2-year secretarial school. So she has a very different background. So growing up in a much less privileged home. So her story is pretty amazing, having, I think, gone from the beginning of her work, working as a secretary, all the way up to becoming the director of a contemporary art gallery. So she's from the art world. But I think I had two remarkable role models in my parents. My dad as an academic. So, I got to understand as a kid what this profession looks like.
Which probably is big help.
And also, and then a mother who became a director. So, what it means to be a leader of an institution.
Oh yeah, that's great. Now, in fact, maybe that answers a question. You moved to Chicago and you went to the University of Chicago Lab School, which I thought was just for University of Chicago kids of faculty. So your father was on the faculty at University of Chicago.
He started his career there, and then my mom's art gallery was at the University of Chicago. So
you were a University of Chicago kid, which explains the lab school. And the lab school is kind of, was it influential? I mean, it's supposed to be a very good school. And
it's a phenomenal school. It was started by John Dewey. Somebody who thought very deeply about education. So the whole University of Chicago and lab school philosophy was to teach kids how to ask the right question and not so much the rote learning of facts. And I think that's so important as a scientist to have that skill set, which is it's all about asking the right question and understanding that there might be multiple ways of getting there. So that was really, I think, something that was very important to that school. And then the other part of the school that I think that I definitely really appreciated it was that it was a very diverse community of kids. And when you're growing up, I don't think you appreciate so much. I mean, that's your reality, but to grow up with that as your reality, I think was also it was a tremendous opportunity.
Well, I love this. I mean, I often say that we should be teaching kids with asking questions, teaching with questions, because, when I was a kid, that you sort of all facts, but now, as I say, you can have more facts in my iPhone than you can, and more misfacts. What you want to do is ask questions. And I think too many teachers and I want to talk to you later about science outreach, which obviously you're going to be involved more in all the time now. But we too often, I think teachers and parents are afraid to say, "I don't know. Let's find out. Let's ask a question." And once I was on some TV program, and it just occurred to me for the first time that every time a kid discovers something, for them, it's the first time in the history of the world that it's been understood, right? And it's a process of discovery where if it's just a bunch of facts that you're told, that's not discovering anything. Yeah, so it sounds like a wonderful school.
It was.
It was a good school, but you were most influenced, you say, by a high school chemistry teacher. Is that right?
I really appreciated what I learned from my high school chemistry teacher. She was one of the very few female teachers I had in my career, and I think the thing that I remember was when I was applying to college. I really wanted to go to MIT, and somebody made the comment, "Oh, they don't accept girls." And I remember talking to her. I think it was actually a college counselor at the time, and she going very upset to her about this. And she just looked at me and she said, "Well, what's the worst they can do? Say no?" And just that understanding that that's an acceptable way to view life. It's so obvious today, but it was such an important lesson at that point in my life.
I've had my stepdaughter, my daughter's past college now, my stepdaughter's in college. But there's so much pressure on kids and on this college stuff that is just, it's the end of the world if I don't get in here. I gotta, and I'm amazed at it. I didn't have to go. I grew up, as I say, in Canada. In Canada, they were all public universities. I basically chose the one I did partly because I wanted to live in that city and a few other reasons. But there was just it didn't seem any pressure. And it's such pressure. And it's kind of sad to see the kids go through it. Are your kids old enough to be in college, or either of them? So
I have one who's a sophomore in college and one who's a freshman in high school.
So you've been through the call. Yeah, you know what it's like.
Yes. It's the craziness.
Yeah. Well, it's great It's great she said that to you. In fact, generally, what's the worst can happen? It doesn't work, and we'll get to that later, actually. I want to talk about that in the context of your work, I think. You often, you're prescient. You assume my next questions. But before I get to MIT, which I want to get to, did you think you might want to go into chemistry because of her or not? Yeah?
Oh, well, there was a moment. Actually, I went to college wanting to be a math major because
I know you did.
And then when I realized math wasn't it was more esoteric than I had understood. There was a moment of a lot of thinking about majors, and chemistry was certainly one of them. But I quickly settled on physics as being the language and focus that really did speak to me.
Yeah, well, I can relate. I had a series of good chemistry teachers too, but and a very weird physics teacher. But I actually did a degree in math and physics, one degree in each.
Great combo.
Yeah. Well, it was at the university I went to, it was sort of two separate degrees and I did it because it seemed like it might be a challenge. But I noticed early on, I still did the math degree, but the difference for me in math, I don't know if this was your feeling. I mean, I was good in math, as obviously you were, but with physics, I could sort of see where I was going. I could see way down the line. And math, I could sort of do it, but I couldn't sort of see way down the line. And I guess for me, that was a big difference. I'm interested to see if you had any kind of similar experience. I mean, I could do the stuff, but what I was going to do next in math, it wasn't so I could see the proof. I could see that. But where the math was necessarily leading wasn't so obvious to me.
Well, I think ultimately, I was really interested in these questions about the universe, which seem mathematical in a sense, because all the questions about boundaries, the beginning, the end, seemed like a math problem. But in fact, I found the physics perspective on this more engaging. So, with a lot of these questions, there's a lot of different approaches. We have sort of silos of majors, but in the real world, there are certainly multiple approaches. So in a sense, you keep trying things, and at one point you decide, this suits me well.
Exactly. It's what resonates with you. I keep telling students they worry too much about a job, but just do what you enjoy and what resonates, and then, we'll worry about the rest later. And also, interestingly, I was chair of a physics department for a decade, or a little over a decade, 12 years. And one of the things that was interesting as we moved, we tried to adjust majors, our major, until we got a joint major in physics, in engineering and other things. And one of the things that's interesting is, I found it again for me too, is that, as you point out, the physics requires the math. But often you really don't at least for me again, really don't appreciate the math until you see it in physics, like vector calculus or something like that. When you see electromagnetism, suddenly it all you get a physical picture that really helps you understand it, in fact.
Absolutely.
I was also surprised by some of the brilliant math students I was with. They all had to take a physics class, and I was amazed, because for me, I thought if you're good at math, then physics is just a breeze. But for them, it wasn't intuitive in any way. It's interesting to see how different people reflect different things. Anyway, you went to math. You went to MIT. You were going to be a math major, which is interesting, and you switched. But before, you said you always wanted to go to MIT. I was interested in why.
Well, I don't know about always, but certainly by the time I was thinking about college, I think by the time I hit high school, it was very clear that I liked math and science. And so when I visited, it was just a school where there was a emphasis. It's clearly it's a techie school.
Yeah.
But it also has. It has an interesting art museum associated with it. It has, there are a lot of sports. You could do sports without being great at them, at least at the time. I mean, these days that's no longer true. I don't know. There's a very strong Greek system, which at the time struck me as something indicative of a place that allowed, kids were having a good time as well as studying hard. And so for me as a prospective college student, I think MIT just looked like a school that would allow me to find my people, as I like to say.
You weren't worried about the pressure. By the way, I did my PhD at MIT. And by the way, I was just looking at the time. I used to teach some undergraduate courses, and we overlapped a little bit. I finished my PhD in 82. You probably graduated MIT in 81, is that right? Maybe? Or 80, 81, 80?
Oh, gosh. Lawrence,
doesn't matter.
Okay, you're going to date me. No, I started MIT in 83.
You started, I'm sorry. Oh, yeah, that's right. My fault. I knew that. You started MIT in 83. Okay, so I'd already moved down the road to Harvard at that point. But I was wondering if maybe there was any interaction. But I know that, were you worried, though, about the pressure? I mean, at MIT, there seems, it seems to be a very high pressure environment that.
Oh gosh, no.
No?
I had gone to a very academic high school, so the University of Chicago Lab Schools, by the time you reach the high school level, it's a very intense high school. So the preparation was tremendous. So I didn't find my freshman year at MIT particularly hard. So okay. I guess I was well prepared and not, and really thinking about, how can I get the best education possible.
Oh, that's great. Okay. By the way, speaking of people having a good time, when I remember when I taught undergraduates at MIT when I was a graduate student for a little while, I met a kid who was a junior at MIT, and he was so proud of the fact that he'd never set foot off the MIT campus in 3 years. So I guess they're all extremes. But did you? By the way,
I definitely took a step off campus.
Yeah. Now, you didn't consider University of Chicago because it was home? I mean, it was a really good. It's a good.
And I'd gone to. I had been associated with the University of Chicago from nursery school through high school. So it was time to.
I agree.
To see a different part of the world.
But it was a fine school in math and science.
Absolutely.
And then you just had this techie focus. You did your MIT, and you switched from math to physics, and then you went to Caltech. So you sort of went to as some people, as MIT might say, the MIT of the West. Caltech would, of course, say MIT is the Caltech of the East. But why Caltech? It could have been, was there a choice or what about Caltech?
Yeah, I had some choices. I wanted to go to Caltech. At that, but again, I was sort of interested in opportunity. And at Caltech, there are so many resources associated with that university.
Oh, yeah, unbelievable.
It seemed hard to beat from just a research facility perspective.
Yeah.
And I think at that point, I also understood that being female, you're also, people will take you more seriously if you have a degree that sort of is considered at the top of the game.
Yeah.
So I think I was cognizant of that aspect, that that would ensure or help me succeed in the long run. And I would definitely make the decision again. It was Caltech is a really intense place.
Yeah.
It's a much smaller place than MIT, so it's got a very different personality than MIT. But the resources are amazing,
and not just for students, but for faculty. I know some of my colleagues are there. One of them, who's an astrophysicist, no longer there, said he was walking down the hall once, and the dean came up to him and said, "We have $300,000 we have to spend. Do you need anything today?" It was like, yeah, it's a different world.
Indeed.
Now, you mentioned that you were interested in the universe. That was one of the reasons you got interested in physics. But did you know you wanted to be go towards astronomy when you were an undergraduate, or did that emerge in your studies from at Caltech?
Oh, it definitely emerged at MIT. So starting in my freshman year there, I got involved in research. So I worked with Professor Hale-Brott in the Center for Space Research, who was an amazing mentor. He got me involved in all sorts of different projects, ranging from the development of a new X-ray satellite. So, working on programming for onboard data acquisition systems. So that was working on my programming chops. And then he also got me involved in a project to use MIT's telescopes to do optical identification of X-ray sources. And so that was it really introduced me for the first time to the world of observational astrophysics. And all of this was focused on stellar mass black holes. So I think at this point, I really came to really love the questions associated with black holes. So in fact, I went to Caltech thinking I wanted to pursue high energy physics studies of black holes. And just at that point, started working with Professor Tom Prince, actually, on a gamma ray satellite. But he had also just joined a completely different project to develop this new technique of speckle imaging with Palomar. And the hope was that you could look at supermassive black holes in the center of other galaxies. So that's what sort of enticed me in that direction. And in the end, the technique wasn't good enough in the optical to do the supermassive search. But it is sort of, I think, what guided my thinking that this would be a really great pursuit if you could get this technology to the point where you could start to ask those questions.
From what I can see, your work has been to use sort of cutting-edge instrumentation. In the case, obviously, the most well-known work is look at the black hole at the center of the galaxy. But you're not an instrumentation. I mean, in the kind of physics, my background is particle physics, as you know, originally, and so there's a big divide between experimentalists and theorists, and much more so, I think, in particle physics. But there's some astrophysicists who build instruments, and then there are others that use them. You utilize the new technology, but were you involved in building anything? I don't know.
So it's I would say one of the things that really attracted me is actually new techniques. So it's almost like a methodology perspective. So I'd say my forte is the development of new methodologies that are enabled by new technologies. So in fact, the project that I was initially interested in with Tom Prince was about using aperture masking with X-ray telescopes. So it's like, how can you do the image reconstruction? So from an algorithm point of view. So at Caltech, I did a lot of work on programming this how do you do speckle imaging? And at the time, it was so computationally intensive that the collaboration was with what was a supercomputer. So Caltech had what was known as the N-Cube. So it's a parallel processing machine. So for me, it was really all about the coding and the figuring out how to extract the information out of the measurements that we were making. I mean, I did very simple modifications of instrumentation in the early days, but more so, I've really collaborated with people on the hardware side to in various ways over the last 2 decades, but ranging from simulations of how various hardware projects would impact the science, but mostly on the back end, the developing the analysis techniques. So I think, this is very much akin to what you find a lot of high energy physicists doing. It really becomes about the interpretation of the measurement and how do you extract the science from the signal that comes directly out of the instrument.
Well, it's interesting for me to hear you talk that your methodology, because that's kind of, if I try and look at your career from afar, I guess that's what I would say. I mean, it looked to me like what you try and do is find new technologies and utilize them. And I want to parse this a little more carefully and go through them, because for most people, they don't know. So I knew the earliest work you did was on speckle interferometry. Can you explain that?
So the concept of speckle imaging is, well, let's just step back. So the problem for the large ground-based telescopes is that we have a turbulent atmosphere, which distorts the wavefronts that are coming through. And the idea of speckle imaging is that you take very, very short exposures that effectively freeze the atmosphere above your telescope. So the atmosphere you can think of it as like a stream. It's basically the jet stream moving above. So you can think of it as those short exposures as an interference pattern, where you have multiple coherent cells above your telescope that allows you to use the same techniques that are used in radio interferometry to analyze these optical and infrared images, and that was really a new idea. So it was super interesting to understand how to handle these thousands and thousands of frames to extract. To pull out the difference between what's the underlying signal and what's the distorting effect of the Earth's atmosphere. But it was a lot of computation. So I like to call it poor man's adaptive optics, because from an instrumentation point of view, it was very simple. All you needed to do is change the optics out front of the existing instrument to make the pixel scale smaller, and then to change the electronics, the readout electronics on the instrument, so that they could keep up with the changing atmosphere. And then the real work then becomes in the analysis. But of course, things have changed so much since then. But it really did us. The first 10 years of our work were all done with speckle imaging.
Yeah, no, I mean, again, as I'm always amazed at what people can do, either experimentalists or observers. And I remember I never heard of speckle interferometry until 1987, when after supernova 1987A, and actually ended up writing a paper with an old friend, Sterling Colgate. But at that time, the speckle imaging had produced another image near supernova 1987A, and no one knew what it was. And we wrote a paper explaining it in obscure terms. I don't think anyone ever, it was obviously spurious, but I don't think anyone ever explained it. But I must admit, I think I know at the time I worked on that paper on this speckle image without having any idea what speckle imaging was. I just knew it worked, or at least supposed to work. But something I did know about early on was adaptive optics. I remember learning about it when I think when I was writing my first book, or when I was a long time, and it was an idea, and I was sure it wouldn't work. I mean, it sounded great. But I thought it's not really. It looks really neat, and behind you are laser beams coming from the observatory, which is of course the image that is related to adaptive optics, and we'll talk about that. And I remember I had a beautiful slide I used in my public presentations of a laser going up. I think it was from Lick, but anyway, at the Lick Observatory, and I thought it sounds great, but how can they really do that? Is it really going to work? So adaptive optics has been very good to you. So and you've been very good to it. So let's walk through adaptive optics, because I think that's really important.
Sure, and adaptive optics, as you alluded to, has been people have been aware of this technology for a long time, but it took quite a while before it became scientifically productive. So in fact, I think I started to, at the beginning of grad school, I was hearing about adaptive optics. But that was a critical moment, because the adaptive optic system, the idea is that you correct for the distorting effects of the Earth's atmosphere in real time with hardware. So you want to introduce an optical element into your instrument that can adapt to the turbulence and how the light gets affected.
Let's just stop for 1 second. And, just assuming people, this is new to many people, the big problem with resolution and observing the sky is the atmosphere between us and the sky. So
absolutely. The atmosphere is the huge problem, the huge headache for imaging anything in the universe. So, what I like to say, it's great for us. It allows us to survive here on Earth, but it is a real headache for doing astrophysics. And so you can think of it, the analogy I like to make is you can think of the atmosphere like a river, like a stream. And if you're trying to look at a pebble at the bottom of the stream, it looks distorted because of that moving water. So the atmosphere is doing something very similar to our ability to detect astrophysical sources. So the next analogy I like to make in terms of trying to understand what the atmosphere is doing and how the adaptive optics system is correcting for it. If you think about a circus funhouse mirror, where your image looks distorted when you look in this curved mirror, that's what the atmosphere is doing. It's taking an image that looks normal and then distorting it. And the goal of the adaptive optics system is to introduce another mirror that has the exact opposite shape to what the atmosphere has done to you, so that you look flat again. So we would say that's conjugate to the atmosphere. So the key elements in the adaptive optics system is called a deformable mirror because it's a mirror that can deform. So it's got little elements that can move up and down very quickly. So that's key. And then some feedback loop that tells that mirror what to do. And so these lasers are key to that knowledge, because you have to look at something bright near your source that tells you what the atmosphere is doing so that you can make those corrections to your little deformable mirror on very, very, very short timescales. We typically run the system at about 1,000 hertz, which means that you're making measurements of what the atmosphere is doing at 1,000 times a second. So you have that's also very demanding from a computational point of view. So the advances in computational ability have been key to enabling adaptive optics. But another part of the story that is it's an interesting story of technology transfer is that it's not only the astronomy and astrophysics community that cares about looking through the atmosphere, but it's also the military community that cares about looking through the atmosphere, both up and down. And it's a community that has far more money than astrophysics will ever have. Mm-hmm. So as this was being advanced in the astronomy and astrophysics community, there was a moment in which it was probably clear within the classified world that enough progress had been made that it was important to declassify. It was worthwhile declassifying this information. So that was the early 90s. So I'd say the astronomy and astrophysics community had just a huge boost when that got declassified. And then it was really about trying to set this up on telescopes that were designed for astronomy and astrophysics. There are a lot of details in these systems, so you have to make the right choices. And I think this is one of the things that Peter Wazinowicz at Keck Observatory did so well, which is to design a system that was really robust. I'd say a lot of the early adaptive optics systems were technically interesting, but not scientifically robust. And the system that Peter built was in just a completely different category.
One thing I want to just step back again, so just so people understand, they may say, well, why the lasers? But the idea is that if you want to know what the atmosphere is doing, you want to know what it's done to a signal that goes through it. So if you start out with a laser whose shape and characteristics that then goes, and what lasers do, and it's kind of neat, if you've never done it with a powerful laser, I've done it with a powerful green laser, you can actually excite elements in the air so you can see the laser beam, and so you can see what the laser is doing through the atmosphere, and that tells you what the atmosphere is.
This picture is actually quite deceptive because all the action is actually happening at the end point.
Exactly.
There's little scattering that happens that lights up the beam, but it's photogenic, but it's not actually the important piece. So these lasers are tuned to a transition, electronic transition in the sodium atoms.
Mm-hmm.
And it happens, just a fluke of nature. There are two flukes of nature. One, we have meteors that come down. And as these meteors come through the atmosphere, they break up and deposit sodium atoms. And those sodium atoms get trapped in a very thin layer that's very high in the atmosphere. So up at 90 kilometers, there's a 4-kilometer layer of sodium atoms. So what these lasers are doing are they're stimulating sodium atoms to shine.
You create fakes. Effectively, you're creating a fake star. That's the point. They excite that in the atmosphere, and the characteristics of that star, because you have how you're exciting it. So in some sense, anyway. Sorry, I'll let you finish, but.
Absolutely. So, in fact, we call it an artificial star. So it's a laser guide. We call them laser guide stars. They're artificial stars. And the light from that source can help us or allows us to correct or to know what the atmosphere is doing. So it's a really important part of this.
You have a stable source, and if the artificial star is flickering, it's due to the atmosphere, basically. The laser's stable, and that. And so by looking at the characteristics of that star, you now know what's happened to the laser beam as it's gone through the atmosphere, and then you can work backwards and deconvolve it. Anyway, I just wanted to make that clear for people, because it still amazes me. And then the idea you do it 1,000 times a second, I don't know, it just blew me away. So when I first heard it, I thought, sounds good. Ain't going to do much, but it sounds neat.
Well, it absolutely. And in fact, for 15 years, I would write proposals to use adaptive optic systems all or everywhere. So when I was a postdoc at Arizona, when I was a new faculty at Lick, which is where the system was up and running before this. And it wasn't until the Keck system was up and running that it became the scientifically robust in my mind. And you can see that when I gave up speckle imaging. So there were 2 years when we did both speckle imaging and AO. And then starting in 2006, we no longer did speckle imaging because it was really ready. It far outperformed actually what we could do with speckle imaging.
And Keck was the place, and that's why I went to Keck. Yeah.
Yes. Now, in fact, that's why I consider UCLA my dream job.
Yeah, because
Sure.
because of Keck, which it's affiliated with.
Yeah.
And you can tell people where the Keck telescope is, just so people may not know. But
okay, so the Keck telescope is located in Hawaii, on the Big Island of Hawaii. It's co-owned by the University of California, Caltech, and Hawaii, and then also NASA. And what made UCLA particularly exciting to me was that UCLA made this investment in hiring faculty that were interested in developing technologies and methodologies that operated at infrared wavelengths. So LA is a place where infrared technology was being developed for the aerospace industry. So it was a strategic, really wise strategic move for UCLA to make. There was the understanding that Keck was coming online, and how could they, as an institution, take on a leadership role.
So I want to again deconvolve this, but in terms not just the atmosphere, in terms of when all this happened. So when you first started making applications to use adaptive optics, what were you thinking of looking at?
So in this narrative or this storyline, so you think optical speckle, thinking about active galactic nuclei didn't work. So I had to I had to decide whether or not I wanted to pursue the science or the technique. Mm-hmm. And I decided that, that new techniques are really would enable you it's a path to new science. So I stuck with the technique rather than the science, but I really kept thinking about, how could we get to the point where we could do the technique and the science of the black holes. But I did make this shift to thinking about star formation, understanding how stars form and under what conditions they might form planetary systems. So I was really interested in binary stars. It was just a science problem that this technique could answer really well. It was an interesting problem. You could make progress. And this is all to say that it was in that phase when adaptive optics was ready for proposals. So this was probably just as I was leaving for postdocs at Arizona. So that's why I went to the University of Arizona. They're really good at this. Mm-hmm. So it was an opportunity to work with Roger Angel. And in fact, Peter Wazinowicz was at the University of Arizona.
Yeah, Roger Angel has been a telescope maker for lens,
right. And Don McCarthy was also doing a lot of speckles. So it was a really exciting group to join as a Hubble Fellow. And that's when I started writing a lot of proposals. I think we had one science paper that came out early on, but it just, this is what you have to do. There's a huge development phase. You have to take the risk and you have to make the investment and you have to have patience, until these technologies are worthwhile or ready. So don't give up too soon. So it was wonderful to be able to work so closely with these adaptive optics teams for so long before and I think that really speaks to the idea that it's a real partnership. I don't view myself as just a user that comes along and uses these facilities, but it's been a real collaboration over many decades now.
It's interesting when you talk about the instrumentation of the science, and the instrumentation is very seductive. And it's the cutting edge technology is really neat and seductive, and it's sometimes easy to lose track of what the science questions you want to ask. And as a theoretical physicist, it was interesting to me because I was a mathematical physicist. I started in very mathematical physics, and I started at MIT. And then it was actually Shelley Glashow, a Nobel Prize-winning physicist who became a friend and collaborator and colleague over time, who once looked at me and said, "There's formalism and there's physics, and you got to know the difference." And suddenly I realized, I'm not really asking physics questions so much as formal mathematical ones, and that changed my life. And focusing on the science when you're in your case, I mean, the wonderful thing about being a theorist versus experimentalist is you can drop it and move on to something else pretty quickly, and so. Yeah, you can try, just like with instrumentation, there's a development phase and you can try it, it may not work, you go to something else. In theory, if you're trying some mathematics doesn't work, it's really easy to switch. But if you're an observer or experimentalist, you've devoted all of this time and energy, and it's harder to, you are making there's a much bigger risk in some sense because the resources are much greater and it takes more time.
Yeah, I mean, there's two sides of that coin. One, you've invested in a really, really unique tool. So if that tool is effective, it is really powerful to think about the scientific problems that can be solved with that tool because you have a uniqueness.
Yeah.
You have a uniqueness in being able to wield that tool, so to speak. So I do think you're getting at something that I talk a lot about with my students, which is that how do you find the right problem to work on? And it's a lot about not only what are you interested in, what is interesting to ask for the community, but what is your ability to solve it?
For me, and one of the hard things for when I've watched graduate students is that they also kind of feel like you have to know everything to do anything, and it's you really have to learn that what you have to learn is something, and get some tools and try and answer a specific question. And you may not understand everything, but and in fact in research that's the point. Often you don't understand what you're doing till the end sometimes.
And in fact, asking the question, how do we know what we know, is really asking the question about scaffolding. I mean, often our current thinking or models are based on a lot of assumptions. So trying to understand how robust those assumptions are is also really an important skill set for finding the opportunities to further our knowledge.
Exactly. Yeah. No. Okay. It's really interesting to see your perspectives on this. But now, at what stage? So you're at Arizona and adaptive optics. You're at one of the key places, understanding it, and now you move to UCLA. Did you go to UCLA directly from Arizona?
Yeah, actually, I spent 1 year in Arizona, and I remember where I was sitting when I read the ad, and thinking, "This is my dream job."
because of Keck? Because of LA? Because of what?
Oh. No, because of Keck. Yeah. I mean,
okay.
I've grown to love LA, but it was the telescope.
Was that your first postdoc in Arizona?
Yeah, I was hired very young. I was 1 year out of a PhD when I was hired at UCLA. So they definitely...
Wow, that's great. They showed great wisdom, didn't they?
Well, I think you can put it a lot of different ways. They definitely took a risk. But I think it was all part of this vision that they had for investing in infrared instrumentation and methodology associated with Keck. So I had this idea that I wanted to use the Keck in a new and different way to apply speckle imaging to Keck. And I think that was, that fit in very nicely with this overarching vision of what's called a cluster hire. So it happened over many years, but not too many years. We hired 5 faculty, and I was number 3 in that. So Eric Becklin and Ian McLean came and set up an infrared lab. So they're actually responsible for building almost all the infrared instrumentation at Keck. And then I was hired, and then James Larkin was hired, and then after that, Mike Fitzgerald. So it's I really like UCLA because it's one of the few institutions I've seen think really strategically, rather than always just having what I call the mall method or the mall approach to faculty hiring, where everybody has their own little shop, but it's completely distinct. There's been a lot of thinking about overall what kinds of problems do we want the faculty to work on or to be thinking about, and that leads to a group of people who have a lot of interest in collaborating with one another. And so it's a department where the whole is greater than the sum of the parts, without a doubt, because of that.
It's important. I mean, I moved to become chair of a department. I had 15 new faculty to hire or something, and it's interesting to be strategic, obviously. On the other hand, my policy always was that to hire good people, and they would do good things. It wasn't necessarily...
Absolutely. But you can do both.
Yeah. And it's also important to realize that someone may be doing something that's hot now, but in 10 years it might not be. And so, because people's careers evolve, and so people who can evolve with the field is important. And yeah, so it's a balance of, as you say, you can do both at the same time, but it's a careful balance when you're hiring. It's always a risk too, of course. But they hired you 1 year out of graduate school, which is amazing. And then when did you... I knew when you started making proposals to look at the black hole, what we now are reasonably certain is a black hole at the center of our galaxy, proposals were turned down. Using adaptive optics, they were turned down. When did you start making those? Sorry.
It was my first year at UCLA. So it was an interesting start. But, to me, it was just so damn obvious that this was going to work, and that Keck it was a combination of Keck and the fact that infrared detectors had improved. So the readout noise of these detectors had also dropped just at the same moment. So I think one needs to understand that both things were happening, and the combination of the two was really what enabled speckle imaging to be so powerful back in the early days. So I joined the faculty in '94, put in the first proposal, it got turned down. But you know what? I'm a huge believer in every challenge is an opportunity, and that that when you face these hiccups along the road, that they ultimately can help you. I mean, first they help you think, well, there's a review committee that's looking at this, and you're trying to convince them to do something new and different. You're young, nobody knows you. So you got to convince this group. You got to go give talks at all the UC campuses, and you got to get to know these people, and you've got to convince them that you know what you're talking about before they invest huge resources in you. So, I mean, it was a real kick in the pants to do that kind of engagement, and it forces you to think deeply about, well, why should they believe you? How do you articulate this? And so I think the science that we ended up doing was probably much better for that early hiccup, and all the other hiccups that happen. I mean, I call them hiccups, like the bumps in the road. The skepticism. I mean, certainly there was skepticism at every stage of this project. And while today it's sort of funny to look back and think, because it seems so obvious that what's been done, but you have to remember the framework that people brought to evaluating these proposals.
Yeah, well, no, let me say quite clearly, it's not obvious. It was never obvious to me that it should work. The challenge is amazing. In fact, I want to walk through that at some point. And by the way, there's a good word for you that I learned from a friend of mine, Frank Wilczek, is chrysotunity.
What is it called?
Yeah, every crisis can be an opportunity.
Oh, chrysotunity. Okay, chrysotunity.
Anyway,
yes.
and I often think of that, and exactly, you can turn it around the right way. Homer Simpson said that. Yes, right. Anyway, just so you know. But, did you really expect this would work? You said it was obvious it would work. You were just sure. You were just sure it would work.
I mean, yes.
Okay, well, we'll get there, because we'll get to all the reasons why
I don't think... Actually, sorry, Lawrence. I would say the first phase of this, which is all we were thinking about in the proposal, would work. And then once it worked, it became clearer that there was so much more that would be done and could be done. So we weren't thinking about where we are today. We were thinking about where we were actually 3 years into this work. And that's all anybody was thinking about.
You could never do. You never know where you're going. If anyone, I always tell people, when you write a grant, you write something for 3 years. But if you're really doing in 3 years what you said you were going to do, then things aren't. You just sort of invent what you think you might do, and then 3 years down the road you see where you're at, and you also see what new things have developed.
Right, and people were already skeptical about the 3 years, the 3-year concept.
What was your goal in the 3 years then?
It was just to do velocity dispersion, so just to measure velocities on the plane of the sky. So we weren't thinking full orbits, and already people were saying, well, the technique won't work, you won't be able to do the images, you won't see stars, and you won't see them move that quickly. So there was a lot of naysayers.
When you say velocity dispersions here, were you thinking about measuring velocity dispersions at the center of the galaxy?
Yeah. Oh, yeah. This was to measure the stars at the center of the galaxy, to ask, is there a supermassive black hole there? And to watch how they move, and to be able to measure how they move. So you want to be able to see them move on the plane of the sky. So even that as a way of probing black holes was new, as opposed to using spectroscopy.
Sure.
But we only had images, so you have to convince people that the speckle imaging will work, and that if you point that there is going to be a star that's close enough that it will feel the gravitational potential of the black hole strongly enough, so that you can see that the stars closer are moving faster than the stars that are further away.
Okay, now we'll get to there, because I want to work slowly there, because I want to get to there to explain to everyone why any sensible person would believe you would never do what you did. But anyway, because that's what's always blown me away. But before we get there, you did something else which I think is remarkable, and that is, I want to talk about this because I think it's important to understand the sort of characteristics of science as a profession. You made this proposal in your first year, but maybe you weren't thinking about this, but one of the things that's so remarkable about the developments that you won the Nobel Prize for is that it's a sort of 25-year project. Okay? Now, one of the big pressures on young faculty is to have results so they can get promoted. There's a huge pressure, publish or perish, and wasn't it also kind of risky to be thinking of potentially, and maybe you weren't at the time, maybe just thinking 3 years down, but a project which would take a long time to get results in terms of your personal career and your likelihood of getting tenure? Wasn't that bold? Or were you just so confident that it didn't matter?
Or ignorant.
Yeah, well...
or naive. I don't know. I mean,
confidence and ignorance often go together, in fact.
I guess I was fortunate enough to have been hired young. I mean, I guess I was, always in the back of your mind, you have basically the academic system is you have 6 years. You have 6 years, and either you're out of a job
yeah,
or, you've got a job for a while. So I guess, 6 years seems like a long time. And I guess it's more than that. It's that you can't keep doing what you've always done in the academic system, because then you're judged as being not creative. So you have to show the ability. You referred to this earlier. When we look for faculty, we look for people who are capable of finding new problems, not just getting stuck and just doing the same old. So, I had a very productive program going on understanding how stars form and under the conditions that, they might form planets. So while I was trying to get the Galactic Center program going, I didn't let go of this other thing, because I viewed it as my bread and butter.
Uh-huh.
It was the logical next step in all of these, from what I did my PhD and then built my postdoc on. I was just sort of stepping taking the next step. But what I really wanted to do was something new. And throughout all of this, the hope had been, can we get to the point where we can apply this to finding supermassive black holes? Originally, I was thinking about at the center of other galaxies, but then it became clear that ours was the place to look. And I was fortunate enough to do a PhD with Gary Neugebauer. So the people talked about the center of the galaxy. I mean, he's one with Eric Becklin who discovered the infrared light from the center of the galaxy. So in a sense, I grew up in a community where that result was very much talked about. So in a sense, this question of how do you get your ideas? You get your ideas because you're listening to what's being said. So I think I was very aware that this would be a very interesting place to try these techniques should the technology get there. So I guess it seemed like a great, exciting opportunity. And you got to try. And I guess I wasn't, maybe what you're learning about me is I have a fair amount of risk tolerance.
Yeah.
And I think at the time, I think I really felt like in science today, it's harder to get funding than to get tenure. Mm-hmm. So tenure seems like a pretty arbitrary, this is how I thought about it at the time. Today, I don't think I have the same attitude about it. But at the time, it was so hard just to come up with the resources to pay the students that was far more central in my brain, and it's a long-term problem.
Yeah, it's a long.
That's not going away after 6 years.
Yeah.
So it's sort of funny. I don't think I was ever really. Tenure didn't weigh heavily in my brain as it probably should have.
When was the first time you realized? I mean, you sort of recognized that there was probably a black hole at the center of the galaxy. When did you learn that? Or
oh gosh, I know exactly when we got really excited about this.
Oh no! I'm not talking about when you with your own work when you really discovered. I want to get there. I'm talking about. I mean, it was in the idea that there could be a black hole in the center of that, and then I want to get to the discovery moment later.
Okay, so yeah, I mean that's a really important question because. The idea of supermassive black holes certainly came from observations of active galactic nuclei, so this small class of galaxies that are, have a lot of activity. But roughly 60 years ago, I guess now, people started to ask whether or not all galaxies could harbor supermassive black holes and not just these extreme examples. And the extreme examples are thought to be extreme because they're thought to be black holes that are accreting a lot of matter. So in a sense, they're being fed a lot.
Yeah.
So this idea that all galaxies harbor a supermassive black hole really speaks to the idea that you can have a black hole that's not being fed and then therefore not being lit up.
Yeah.
So that notion has been around for a very long time. And then I think it got exciting in the center of our own galaxy when an unusual radio source was discovered. It's got a name, Sagittarius A star is how people refer to it. Sagittarius because it's in the constellation of Sagittarius. Mm-hmm. A because it was a bright radio source, so we usually, it's like ABC in order of brightness. And then the star part is just a really lousy part of the name because it was really Sag A asterisk, taken from nuclear physics, where asterisk is excited state. So it was really meant to say this emission doesn't look like stars; it looks like excited gas. So it really is Sag A, not a star. So we were really asking. Is this radio source, this weird radio source, the black hole? So we knew where to point. And I should also say the density of stars also gets higher as you go to the center of the galaxy. So you look for the point or the region where the stellar density, the crowding of stars is highest. And that's also where the black hole is. So we have a big field of view and we capture both things.
Yeah, no, okay. And I think actually my good friend Martin Rees was one of the people early on who theoretically was trying to argue that perhaps that radio source, he did a lot of work on radio sources and quasars and black holes. So there was sort of theoretical motivation of thinking that it might be, and that sort of was percolating in the background.
Absolutely. Yeah. I mean, there's a very famous paper by Lynden Bell and Rees that made that suggestion, I think in the 70s.
And were you aware of it?
Yeah.
Okay. Okay.
So absolutely. So this is the basis of a proposal. Like, we know where to look. This is where we want to look. We want to answer this question. But at the same time, there were people who were pointing to the fact that they're in the vicinity, there were young stars, and that star formations should be suppressed if there's a black hole. So there was also a school of thought that said, it doesn't look like there's a black hole at the center of our own galaxy, which I think is part of the skepticism that existed when we first, in the sort of late 80s, early 90s.
It's important that people are skeptical of things, and it's important because the good problems are the ones people are skeptical about. But given that I really do want to get to science next, but I do want to hit this thing a little bit more about you're a particular person who's risk, not risk averse and doesn't mind taking risks, and theoretically, and I can relate to that in my theoretical work. But the example I think of is Dirac, who there's a wonderful story which I won't go into, that when Dirac was first, I think at Bohr's lab, and I think Rutherford wrote him a letter about Dirac, and basically Dirac didn't talk to anyone that year, and just sat in his office. In the current climate, he would never have gotten a job. Okay, but and I think the story I know, which may be apocryphal, is that Bohr complained to Rutherford, and Rutherford told him a joke, which I won't tell you about, but it involves a parrot. And, I'll give you the punchline that, these parrots, and they're beautiful ones. And the guy in the store says, that's $500. But this parrot here, what does it do? It's not beautiful. It doesn't talk. And, it's $25,000. And the guy says, how come it's $25,000? And he said, that parrot thinks. It's a great story, which I've often, and I would have, you can play out the joke longer, but, Dirac was thinking, and I often wonder whether that kind of, in the current world, that kind of, if you're a theorist, you're thinking, or an experimentalist, you're building, you're working, whether we make it impossible or largely impossible for people to do that, to sit back early in their career and not necessarily be quote unquote productive.
What I like to tell my students is find good science and do it. Because that's what matters at the end of the day.
Exactly. And if you're not doing the science you want to do that you think is important, you're not going to do a good job anyway. So be given and I think your career is a perfect example for me. And one of the reasons I wanted to explore it so carefully is to find the good science, do it, and be brave enough to do it. And, because it's what you want to do. And as again, I quoted Feynman in one of my books, and people said it wasn't Feynman. I knew it wasn't Feynman, but Feynman would say, damn the torpedoes, full speed ahead. And I think that's the point. You just got to do what you got to do.
Mm-hmm. And we can get sucked into this idea that lots of incremental papers are better than a few transformational papers. So I think at the end of the day, the goal is really to move the knowledge frontier forward. And it doesn't matter. I think that's a challenge for the rest of us who are evaluating younger faculty careers or grants, is really to look for the opportunities to make deep progress.
Absolutely. But it's also worth recognizing those opportunities are few and far between. We all look for them, but when they actually occur, it's few and far between. I meant many papers which, if nature was smart enough to adopt those ideas, it would have been great. But you've got to nevertheless keep working. And again, I in my own mind, I remember when I was a junior fellow at Harvard, and I remember Shelley Glashow again would say, got to find some pieces of grizzle too. You got to find something to work on.
Right.
And it may not be, you can't always change the world. Yeah, it's hard to make progress. And so you've got to find problems to work on, and you don't know, and often you don't know where things are going to lead. So it's a combination. And
so I guess I think I've always had the just keep going on something project and the longer term risk thing.
That's a wonderful thing to have.
Yeah. And then in the end, this project with the Galactic Center has yielded so many different short-term science projects that it's also supported the longer-term goals.
Yeah, so and that's a wonderfully lucky thing.
It's unique because it's such a complex, scientifically rich field that the data that we can take can serve multiple scientific purposes.
Great. Okay. Well, we're going to get to the science more, but I think it's important especially for young people who are beginning to think about these things, to get perspectives on on their career if they want to be scientists, and what the challenges, opportunities, and crisisopportunities are. But now I want to take us through eventually to the discovery process. Take us through from the time the proposal was sort of first funded in its initial stages, and maybe and in the context of that, I want to maybe let's step back and talk about the real challenge here. And maybe you've produced one of the movies that I probably showed, I think maybe once when you're in the audience there. But if you're looking at the night sky, like the fake night sky behind you, you're not seeing the center of the galaxy. You're not even seeing the stars. I mean, the amount of the level to which you have to pierce and then pierce and then pierce and then pierce in order to get there is remarkable. And so while it may have seemed obvious you could do it, I think it give people a perspective of the actual size of the region that you were trying to look at. Then we'll proceed through the historical discovery.
I mean, I think one thing to recognize is that our whole field of view is usually just a few pixels from the point of view of a typical astronomer. So we have a very large magnifying glass, so to speak, on this region.
Can you say in terms of on a language which we may have to explain, arc seconds or something?
So it's the field of view is 10 arc seconds.
So just so people get a idea, an arc second is you divide the sky into degrees, but an arc second is 1/3600th of a degree, right? Isn't it? Because you think of as 60 arc seconds in an arc minute and 60 arc minutes in a degree. Is that correct?
Yeah. So it's on order of, I mean, the light takes about a year to get across our field of view. Uh-huh. So that's I don't know, again, in terms of, does that give us any better of a sense?
Well, maybe, but I think for people realizing you're looking at all of the action that you're trying to ascertain is 1/3600th of a degree, or a few 3600ths of a degree across. And you're looking at something that's 100,000 light years away, more or less. Or okay.
The moon, it's in the sky. It's half a degree.
Yeah.
And the other way to think about a half degree is if you stick your thumb out at arm's length, that's a half a degree, and you can fit 40,000 times our field of view across the moon.
So it's smaller. Another way, I guess, in that term, and I hadn't thought of it. I'll have to see if I can come up with an analogy. It'd be interesting to think about. It's the size of a very small crater on the moon. Very, very small crater on the moon, maybe that you'd have to look at or something like that. But it's also much further away and a lot more stuff between us and it than between us and the moon.
I think it's much smaller than a crater. It might be the small size. Well, I'm going to look this up. Yeah,
it's a good thing. It's a good thing to do because we can figure out the size of the moon divided by 40,000. We can do that. And
I'm not going to do it trying to speak to you real time, though.
No. But it may be much smaller. It's interesting. It's probably smaller than, smaller than crater. And I wonder if it compares to one of the scientific instruments in Apollo 11.
Yeah, that's what I was just wondering. It's like, okay, what was it? What thing have we put there?
This is a homework problem for people by watching this. You can do this yourself.
Don't air this. It's like
I think maybe I might air some of it because I think it's important for realize how scientists start to think about things. It's the same reason why I used to like to sometimes go into recitation sections without having looked at the problem that I was going to solve, because I thought it would be interesting for the students to see hold on, okay, let me try this, to see the thought process. It's sort of nice because we present science as if it's all, in fact, in history, your result will be presented as after the fact, an obvious thing to have done, but that's not the way science goes, right? I mean, it's not done by logic. History sort of proceeds in different ways, and it looks like you're doing a calculation well.
Okay, yes, you're... Okay, it's a 40th of a mile.
It's a 40th of a mile, so it's much bigger than it is. So it is a crater. Okay, I win. Okay. Okay, we'll see. The prize. We'll see how much of this we are, but it'll be. Anyway, it's fun. Okay. Anyway, bottom line is, but it's a 40. It's like a small crater, but as I say, small crater located between us and it, a lot of stuff, not just the atmosphere, but much of the galaxy. So take us through now, having done that, from the first proposal to the discovery.
once we convinced people that the technique would actually work, the trick was to go to the telescope and collect all this data that would result in spectral images being done. And the thing I like to share about this is that there's a lot of software development behind this. So in fact, it took us a year to perfect the techniques to make an image at the galactic center. It was much more complicated than the binary stars because there are a lot of stars. So it's just from an imaging perspective, it's a harder problem. The second image that we got was in '96. Took us a month to analyze the data fully. But then you have 2 points. And with 2 points separated by a year, you can make a line and figure out how fast the stars are going.
Yeah.
You don't know your uncertainties very well, but you know they're moving. So already in '96, we knew something was exciting. But we decided that we wanted to take one more measurement to really understand how well we knew things. In other words, to understand our uncertainties. And I think this is super important, both in terms of understanding how science is done and really the value system that my group has, or my own value system, which is, you want to convince yourself of your uncertainties. So I take the risk of time. So we waited another year to get a third measurement, and 3 points, you get the line, and you know how well you know the line, you know your uncertainties.
Yeah.
And so that's when we published after we got that third measurement. And then it takes about a year for the publication process to happen. So that was getting to this velocity dispersion.
For people who don't know about velocity dispersions, and when you publish, what you were measuring was the speed of that star, just so to put it in a way. And that, so go on.
And I mean, at that point, it was only about 100 stars. So you're looking at the speeds from, trying to measure a line through these points. So you have basically X and Y and time.
Yeah.
So you can make X versus time and Y versus time and get the slope and see how fast things are moving. And they're hauling. I mean, you didn't need a computer to tell you that these things were moving fast.
This, again, for the fact that they're hauling is important because it means they're moving darn fast. I was going to use a different word, but they're moving very fast. And that tells you something. Why? Just so people.
It tells you something because if there's a central point, there's a central mass that's driving these things to move. Things are going to move faster close to it than further away. So the key is actually not only that they're moving fast, but that you see close by that they're moving much faster than the stars that are further away. So it's the comparison of your entire set that you see this drop off, very predicted drop off, where it's actually 1 over the distance squared from the middle, that tells you that something in the middle is dominating how everything is moving. It's driving all this motion. So that was super exciting.
It's very exciting. And so just so people get an idea of how of things and how fast they move, and our sun is moving around the galaxy at 200 kilometers per second. The Earth is moving around our sun at 30 kilometers per second about. What were the speeds that you were measuring of these stars in those units?
Thousands of kilometers per second.
And then suddenly you see, when you see thousands versus hundreds, you know you've got something right, special.
But it's actually, the drop off happened within our data set. So you could go from thousands down to roughly 100 within the data set. So you get this beautiful curve. But you do it statistically, because this is an early approach. No individual star tells you the answer. You have to take averages of sets of stars. And that's important because that means that the first stage, there were underlying assumptions about the kinds of orbits that these stars were on and the distribution of stars. So it was exciting. But there were naysayers. There were naysayers that said, you can get things moving fast for all sorts of different reasons. And it's fabulous that there were naysayers because that's why we kept going.
Yeah.
The next thing that is becomes clear is that you should see an acceleration. Just keep watching them. If you believe that there is a 4 million or times the mass of the sun black hole at the middle, then ultimately things should deviate from a straight line. And that took us, I think we needed 2 more years of data. We had 98, 99. Yeah. And by 99, the first 3 stars started to show the deviation. And they were believable. And again, because there's all sorts of ways in which these measurements can go astray and not be true. But the accelerations the direction of acceleration was all pointed to the same point. So these were three things. And I think that was like pointing, that's where the black hole is. So we could figure out where the black hole was way more precisely than ever before. And it was consistent with this radio source. So that alignment, actually, that was a big piece in that paper that came out in roughly, I think in 2000. And it was the aha moment for realizing what kind of periods these stars that we were measuring could be on. And the realization that while my favorite star is SO2, it's actually the one that won the race, not SO1. So SO1 was closer to where we think the black hole is, but SO2 was on an elliptical orbit. So it was just hanging out at furthest approach and had a quite short period.
And it's worth pointing out that SO2 is the one where you basically, if you see the images in the movies, you can see it do an orbit, which is just amazing. And Kepler would be so happy. You see an elliptical orbit. In fact, I want to go back to, because really just so people realize the significance of all the accelerations pointing out, and you said something, but I have to ask if you said it goes down to 1/r squared. But Kepler told us that the square of the velocity of planets as they move around the sun falls off as the square of the velocity falls off as 1 over their distance. So presumably that's what you found, right? That the fall off.
Oh, I'm so sorry.
Velocity was the square root of.
Yes, right. I'm thinking accelerations. Sorry, my bad.
Presumably you can measure.
Oh my God.
Just as no worries. No worries. I wanted to just clarify that. That's But it wasn't clarifying. That's the key point. But you could, in principle, do what we can do for the sun, which is this beautiful Keplerian plot where you can measure the velocities of planets as they go away from the sun, and it falls off on this beautiful square root of r curve. And presumably that's exactly what you could see around this dark object, right?
Yeah, absolutely. So it followed that relationship beautifully, and you need a large set of stars to show that if you're only measuring velocities.
And if you don't have the three-dimensional motion, then you just have their line of sight motion. You have to average out for things as well. But
right.
But also the fact is, and this was Newton's great discovery for people who are new in science, is that when to make something go around an object, you don't pull it around. You pull it towards the center. As anyone who has a rope realizes. And so and since force is proportional to acceleration, that means any object going around another object is accelerating towards the center. So if you could show that these objects are just not randomly accelerating, but they're always accelerating towards the same point, hey, that is sort of the Newtonian kind of gotcha moment. So I just wanted to fill in that.
Thank you for filling in and catching my
no
brain glitch.
No, not just that, but the fact that it's easier for us to say the acceleration's all to the same point, but the significance of that may not be obvious until you think about if you're not familiar with the, sort of Newton's laws and so on. And it's really
right. It's such a beautiful demonstration of Newton's laws.
But of course, it's actually a beautiful demonstration of general relativity, which we'll get to. Which is
what I was actually thinking is that you can bring it into an early physics or astronomy class to demonstrate this. And there's so much you can learn. I mean, it was interesting just to do the simple thought process of if you've gone from velocity to accelerations, because people hadn't thought about measuring black holes from just acceleration measurements.
Yeah.
What do you learn? And so it was really fun to think about, what information content do you get for each step forward, given that it's not a tried and true set of steps that people had taken before. So it was really fun, just kind of simply think through the simple logic of what comes from each of these things. But at the point where you realize that the orbits are short, it becomes clear that you should keep going. And
in your life, because it's not your children's children that are going to be able to say, you can say, oh, that's, and for some projects, I know it's your children's children that are going to get to see it. But the other thing that's interesting when you say you could put it as an undergraduate problem, I think it's really important. I often use that Keplerian motion stuff when I'm talking introductory physics to talk about the discovery of dark matter. Because kids get this sense that, that stuff was done 200 years ago, by dead white men, and it's not interesting. And the point is that it's interesting, and it actually allows you to do cutting edge science, whether it's dark matter or in this case, the black holes. And it's a wonderful thing. But
it's been beautiful in terms of the simplicity of the physics.
Now you say, so two things around 2000. Was it around 2000 that you realized, hey, we can do the orbit? Was that?
So once you get the accelerations, you realize the value of the acceleration, you realize, oh, these could be short. Like 10 years is not unreasonable. And at that point, people start writing papers, and it occurs to us as well that once you get to orbits and they're that short, you can do all sorts of interesting tests of direct tests of
general
relativity.
And we will get there. But so was that the same paper that you, once you have the accelerations, you can then guess the mass of the black hole? Not guess. You can estimate the mass of the black hole. Was that the paper in which you estimated the mass of the black hole?
Well, so it turns out the velocities already gave you this statistical approach. And in fact, the answer that everybody was giving, I mean, my group and then the group that's out of the Max Planck in Germany, was 2.6 million. We were both saying this very precisely, actually. It's interesting in terms of, you can get statistical errors, but if your technique's wrong or not quite accurate, because there are all these underlying assumptions. So when you get accelerations, you don't get mass, you get density.
Yeah.
So that was interesting. So you can't make progress with a mass estimation. You just start to learn that, if your mass really continues to be that number, the orbits are going to be short. So the orbits is what nailed the mass. And it was an interesting moment when we realized, the orbits are telling us it's 4. The answer is 4 million. Because we were saying 2.6 plus or minus 0.2 million. So
points out for people the importance of systematic errors, not just statistical errors in astronomy.
Well, the analogy I like to make is it's like being a teenager and saying things very emphatically. Yeah. It's just you don't have the whole picture. So we definitely learned that there are some there was something not quite right about the approach that we were taking, and yet that's the approach to all other supermassive black holes in other galaxies. So I think it was an important cautionary tale for other studies.
So do you think that means that there's some systematic correction that you should apply to get the right mass of supermassive black holes in other galaxies, or have people done other tests?
Well, I think it's that you have to be careful because you're making assumptions about the kinds of orbits the stars that you're looking at are on, and the distribution of stars, like the density distribution, how concentrated they are. And so just when you make those assumptions, you have to never forget that's an assumption. Yeah. And we tend to it's just an overall thing that gets done in any thing when you take a technique and you forget that there are underlying assumptions, and if you forget that, you make systematic errors.
So the first excitement was the three stars, the 2000 paper, which made it clear you've got acceleration at the same point. It's clear that there's a black hole. That's kind of the black hole discovery paper, you call it, I guess, in 2000. And then how long was it?
I'd say it was like 90, for us it was a 98 velocity dispersion. We called that the black hole discovery, but it was with velocity dispersion. And I'd say we increased the density of dark matter by a factor of 1,000 compared to what came before. The accelerations.
You increase the density of dark matter?
Inferred dark matter.
The
inferred dark matter density. In other words, how small a region you've confined the mass to. So it was a factor of 1,000 from where we started with just velocity dispersion. So that was an important paper or set of papers. But there was skepticism. So then the next piece, what I call phase 2, was the accelerations. But the key papers, I think, were when we got to the orbits. So you knew you could get to the orbits in the 2000 work. And then the actual orbits.
Which is when was the first paper?
Early 2000s.
Okay.
And in fact, the first time I remember talking about this result was in July 2002 at Martin Rees's birthday party. So that was exciting.
I remember, it was around, I'm trying to remember, but it was around when you first heard this exciting discovery that you could actually measure stars moving around. And it was probably sometime that I became cognizant of it, sometime late 90s, first learning about it. And then probably it was around 2002 when I first saw the first sort of curves. And so what, among all the different steps, the dispersion, the acceleration, the realization of the orbits, what was the most exciting for you, if there was?
It's interesting to ask about the moments. There were so many moments. Realizing that you can make an image.
Yeah.
realizing that the velocities are following this predicted relationship, but probably the accelerations. I mean, the accelerations were a game changer, that you knew you were going to get to this orbit phase. And just the simplicity of realizing that it's all working. It all works so beautifully. That was a really exciting moment.
Now, you were able to do this because you were at Keck, or the telescope was at Keck, because you were using the best instrument for the time and also the best, adaptive optics. Yet everything came together.
Even through the very first orbit, to be fair, was not with adaptive optics. So orbits and adaptive optics kind of came together. And it was super important because while you can get a full orbit with just images, you don't have the third dimension of motion. And adaptive optics allows you to take spectra as well as images. So to measure how things move along your line of sight.
Which is important, obviously. Yeah, because if you're just looking, you never know if the optic's going that or that way. Okay, now you were doing this, but you weren't the only one doing it, clearly. And when did you become aware of the competition, and how did that impact on you?
Pretty much the first year, and I think there's always competition in science.
Yeah, there always is. There are all these people doing stuff, but
if there's an opportunity, there's a moment where this opens up, there's usually multiple people who go for it. So it would be a really weird world in which you didn't have competition.
Well, I think it's important to say, the reason I'll interrupt for a second, is because people have this illusion, of an Einstein sitting alone in a room doing stuff. And the point is that science is a community, and ideas and techniques develop, and therefore it's the rule rather than the exception that people independently come to recognize an important problem, totally independently without talking about it, because it's in the gestalt, it's in the air somehow, because all these things, and it's so science is a community activity in many ways, and I wanted to just push that.
Absolutely, I think that's super important to recognize. There have been two groups that have been at this for a very long time, and it's been a very healthy or helpful for these two groups to exist, at least from my perspective. I've really appreciated it. It's not without complexity. I mean, that's for sure. Over time, there's been pressures at various points to merge or join forces.
Yeah.
I guess I've resisted that over time, because I think that there's so much value to having two groups come to the same conclusion. There's a lot of, while they're independent, as you point out, like we go to conferences, we share our results. So we're constantly learning from one another. But it's really wonderful to have another group who really understands where the potholes could be, who can really evaluate your work. And yet, doing it independently allows us some freedom of thought to maybe approach some things from a slightly different point of view. We're also using different telescopes and different instrumentation. So it's an opportunity, there's reasons why you might not come to the same conclusion. And over time, it's been great and very helpful to have the two groups agree when they do agree, and when we don't agree, it tells you we got to think about this more carefully.
Well, that generally in science, especially for new observations, unexpected ones, you want to have. In many cases, you don't even accept the observation unless there's a confirmation. Certainly, it depends. In particle physics, often there are two large detectors and an accelerator for precisely that region, because if they both don't see the phenomena, then you begin to worry. And in that, But you mentioned the point, different telescope, different instrumentation. So you had the advantage of Keck and the instrumentation there. What was the, if you want to call it, the competitive advantage that Reiner's group, where were they working, and what did they have that you wish you had at the time?
I have to say there was a phase of this where, it's very hard, it's not to get wrapped up in the who's first
of course.
Business. But it's really healthy if you can get away from it and just focus on getting the science right. And I think that's something that I've certainly tried to focus on. Just get the science right.
Well, if you can keep doing that.
Oh my goodness, we have so much exciting stuff coming on, coming coming up. I don't think I can ignore the science.
That's great. That's wonderful. It's capping at a good time for you then, because if you've got a lot of good meat to chew, then the distractions won't bother you too much. But at the present time, at least I read something at Reiner said that they have some advantage in some instrumentation right now that they're very excited about.
Oh, well, this is interesting in terms of technology. So one of the things that they've worked on is an instrument called gravity. So it's an interferometer. It's separate telescopes. So it's combining the light from separate telescopes to get the resolution as if you had a large telescope.
Yeah.
Now, there's always this interesting balancing act between resolution and dynamic range. So the thing that you give up if you don't have a filled aperture is dynamic range. So you can't see things that are very faint near things that are brighter. And at the Galactic Center, there's tremendous dynamic range. So my emphasis has been on developing new adaptive optic systems that will get us to the long term of the 30-meter telescope. So hopefully it's not too long. So it doesn't get you to quite the resolution, but it gets you much higher dynamic range. So they're just two different approaches, and I'm sure they're going to learn a lot.
Okay, well, and it's good to, but as you point out, it's good to have different strategies because sometimes they're complementary and sometimes you never know which takes off. What can we learn? Okay, so people say, okay, great, black hole, big deal. What can we learn now based on what we have? I know I'll anticipate. I'll just say, for example, now you can measure the speed with spectroscopy, the speed of stars, the redshift, and you can measure things like what's called a gravitational redshift, which comes from general relativity. You're looking at differences from Newton now, and also and you can also look at how stars or objects or gas gets eaten or destroyed by black hole. So why don't you go through relatively quickly the kind of most exciting things you can learn about black holes and about science in maybe 3 or 4 minutes?
So there are two different directions big overarching directions that I'm super interested in about supermassive black holes. One is their astrophysical role in the formation and evolution of galaxy, and then the other is what they can teach us about how gravity works near a supermassive black hole. So just to briefly say, the astrophysics is really interesting because almost everything that we predicted about the stellar population is inconsistent with what we've seen. So this is opening up all sorts of questions about how stars form in this very extreme environment. Shouldn't happen, yet it does. And then we're seeing stars being torn apart as they pass through near the black hole. And that suggests that these objects are much larger by like a factor of 100 than anything we predicted. So that's gotten us thinking about how black holes can drive pairs of stars to merge. And that's exciting because it's a connection to the gravitational wave community. So there are unexpected connections that come out of this that I find intellectually quite interesting.
Oh, wonderful.
The gravitational physics side of the house, these stars, now that we've got full orbits of at least one, measured from both the imaging and the spectroscopic side, allow us to do new direct tests of how gravity works near a supermassive black hole, providing us with, the first direct test of Einstein's theory of general relativity near supermassive objects. The first test that became accessible to us was the one of the gravitational redshift. And so that describes how the mixing of space-time affects the photons, the light the passage of light from the star to our telescope. So that was measured at closest approach by the black hole.
Yeah.
So the star went through closest approach in 2018. So 2018 was a really exciting year for us. There were 3 key moments that had to be detected, one in April, one in May, and one in September. So in fact, our strategy was to wait for all 3 events to happen before we published. And that was just consistent with our style of collect all the information, figure out the science, and then publish. And then the next thing that's emerging is what's known as the precession of the periapse, which measures how the object itself moves through space-time rather than the photon. And you expect these orbits then to make not to come back to the same place. So general relativity tells us that it should overshoot. So it should be make a pattern like a kid's spiral graph.
And let's just step back and point out for people that was the calculation that Einstein did that he said caused his heart to almost stop. When the first time he did general relativity, the perihelion of Mercury precesses and which he knew about amazingly, and it's important. It wasn't just pure theory. He saw that his theory could actually explain it, and that's when he said, I got it. And so that moment, anyway.
That's awesome. It's awesome because that's the same phenomena that we're trying to explore near the supermassive black hole. So rather than the sun, which is a one solar mass object, something that's 1 million to 1 billion times the mass of the sun.
What do you think is possible? It's hard to ask, but I mean, because you never know until you try.
Possible.
I mean, in terms of pushing this technology. Both. What's your dream experiment and what's the next level of instrumentation? Yeah.
We are only seeing this tip of the iceberg. We see the brightest stars that are there. And so we're delighted, but it would be like trying to understand the economy by only being able to see the largest financial transaction. It's the small ones that are so key. So you cannot see a typical star like the sun at the center of the galaxy. We don't have the resolution. So I'm really excited about pushing forward with adaptive optics, both to correct all what the atmosphere does. We only correct 30% of the problem today. Okay. And in fact, it gets much worse when you go to a larger telescope. So basically, this new technology increases the scientific reach of the Keck Observatory and mitigates technical risk for future telescopes, such as the 30-meter telescope.
So that'll be pushing. Really, that's the next step eventually, pushing adaptive optics to become better and better. And seeing more stars. So do you think the best is yet to come?
I do. I'm really excited about the future.
Well, that's a good feeling because, it's been pretty good so far. So it's always good to have that attitude anyway to push you forward. I want to go back to the Nobel Prize, which I didn't want to focus on here because it's, as you point out, it's the science that matters and prizes are kind of arbitrary and stuff. But of course, if I ask you like all journalists ask, which I don't want to be, were you surprised? You're going to say yes. But were you more surprised because you won the Crawford Prize? It used to be. In 2012, you won the Crawford Prize, and it used to be in the field, the Crawford Prize was given to those areas where they weren't going to give a Nobel Prize. And so it was, I don't know whether they call it consolation prize, but is often that way because they didn't used to, in fact, have as many prizes in astronomy. In fact, we'll get there. But were you more surprised because of that, or were you blown away, or were you say, okay, well, maybe this was going to happen?
I stopped at one point thinking along with the, who's first with the German group. Once you sort of move away from the worrying about who's first, who's recognized, and focus on the science, it's a very freeing moment. It doesn't mean you're not aware because, of course, people talk about it. There's just chatter chatter that tells you either, it's kind of like gossip. It's science gossip, right?
Yeah, of course it
is.
Who's
going to win? Who won't win? Yeah, and you hear this, right? People will tell you, oh, maybe you'll get it. And some people will say you'll never get it. And what do you do with gossip? You ignore it.
If you're smart.
You're smart. Like, there's very little value. So
and the world is all too occupied with gossip. So
my goodness.
If you can avoid it.
There's so much really great science out there. And there's so much great science that will never be recognized in this way. So there's far more great science than awards. So if one gets too you'll always be disappointed if you get wrapped up around this question. So I think I felt, quite frankly, too busy to get overly wrapped up with this.
So you weren't every October, 6th going, okay.
I was asleep.
Yeah.
My cell phone was on Do Not Disturb.
Excellent. And as you point out, there are a lot more people. I like to say that and I know, having been involved in the Nobel Committee in different ways for a long time, they do a very good job. So generally, the people who win the Nobel Prize, the work they do deserves it. But the thing is, there's a lot of people who do work that may have deserved it that don't get it. So it's not as if they choose the wrong people. It's just there's just not.
And in fact, above all else, I'd say this is one of the things that the Nobel Prize is really well known for, which is a very careful process.
Unbelievably careful process, having been involved in it.
It takes years, I think, from the first time people are suggested as a potential nomination. And there's a very careful vetting with the worldwide community. So I actually really respect what the Nobel Foundation does in terms of this worldwide engagement of the work. It's not just one committee. It's really, there is an ultimate committee, as far as I can understand this process, but it seems like there's a really interesting process that engages people from all around the world.
They're vet. And then, for a decade I was a nominator, but I just watched and was there. And so, they're very careful, but it's still a prize. But what I wanted to point out, and really what I wanted to get at, was not so much that aspect, but what has been interesting science-wise, in a sense, the Nobel Prize was generally not given in astronomy, with very few exceptions. There was pulsars, there was the nuclear astrophysics, but generally kind of astronomy was a field that wasn't. And then suddenly in the last few years, Hubble didn't get the Nobel Prize, Vera Rubin didn't, but suddenly it's like now because as astronomy has merged more with physics, which has really happened. When I was a student, I never took an astronomy course. Let me point that out, because it was totally separate from physics. And then it started to merge, and I now do, physics and astronomy, or astrophysics. And then in the last bunch of years, gravitational waves, Jim Peebles and cosmology, planets discoveries. Do you think this is the most exciting field discovery now of science, of physics? That you think this trend is going to continue?
Well, I think astronomy and astrophysics is a really exciting field because the technology is evolving in such a way that there's tremendous impact in this field. I also think it's interesting in terms of what we think of as astronomy and what we think of physics. All my degrees are actually in physics, and so when do you call yourself an astronomer? When do you call yourself an astrophysicist? And I'll tell you my definition of this, because this is what I used to do on a plane. Okay. If you want to talk to the person sitting next to you, you tell them you're an astronomer. If you don't want to talk to them, you tell them you're a physicist. And if you want a short conversation, you tell them you're an astrophysicist. But I'm quite frankly comfortable with all titles.
Yeah, me too. I've as a professor of astronomy for many years, but I never took a course. But it's nice to see when fields merge. It was that way. At one point in my PhD, I thought of doing biophysics, and a very influential doctor once told me, don't do biophysics because it's not of interest to biologists and it's not of interest to physicists. And that was true 30 years ago, 35 years ago. But now it's like totally changed. And it's nice to see these fields merge. It's all science. And it's great to have, there's a lot of things I wanted to do in this conversation, as I hope you realize, to talk about the nature of science. And it's been fun to do that. And I know that that you have now an interest in, I hope you have the opportunity to continue to talk about science. And there's competing demands on someone. It's been on my life the whole time. I've had these competing demands. But you said something about new responsibilities. And so what among those new responsibilities are you most excited about now that you're in this position?
Well, I think it's sort of funny. I often think about we were talking about risk before. So there's something about, somebody once described me as somebody who takes calculated risk. And so I think there's some thinking about what you do and when and why. And that, I think, is similar to thinking about responsibility. So as we grow up sort of in our academic profession, we have to take on more responsibility. And there's all sorts of things that one can do in terms of taking on shouldering that responsibility within the field. And I think with this kind of recognition comes tremendous opportunity, but also tremendous responsibility, because
Spider-Man said that. Anyway,
I'm channeling Spider-Man.
Anyway.
My kids would love that.
Yeah.
Yes, I do. I do think very carefully, and I think part of it is taking it slowly, because I'm still incredibly excited about the science, and so one of the opportunities is it sheds light. This prize sheds the light on the research, and will hopefully enable us to continue to go forward. But there's all sorts of other issues associated with advancing the technology. Yeah. And these instruments and these telescopes are tremendously expensive, and they're complicated. There's complex partnerships. So I think I've always worked quite a bit in that area. And then I've always had a passion for encouraging young women into the sciences. This has been true, I don't know, since graduate school, when I think I really came to appreciate the importance of role models. And I think for me, so far, I've really focused on this mostly by trying to engage trying to be willing to do public engagement, because I think just seeing somebody who looks like you can make a huge difference. And in fact, at UC, actually, this started in graduate school, right? This did start in graduate school. So when I first started to teach, I really decided to always teach at the undergrad, like the first year introductory level. It's the place where you can affect both the young men and the young women in terms of the notion of what does a scientist look like. And so I think that's the way in which I can continue to help move. So that with the Nobel Prize comes a lot of public engagement opportunities. So to share the work, to share the process, and to share just how exciting the field really is.
Well, and I hope that's one of the reasons I want to have this. So you can use this, as an opportunity to share. That's why one of the reasons why I do this whole thing is the ability to share. And I knew you'd be a wonderful person to share the excitement with. And it has been just delightful. It's always delightful to talk to you, and I really, really appreciate it. And by the way, I will end by saying that if you want to explain to people about the atmosphere and the way it messes things up, use that background you have on a Zoom meeting and move your hands back and forth because it
does it pretty well.
Yeah, I was thinking there's an example right then and there. But anyway, it's truly. It's great. I'm happy for you. Best of luck. It is truly, genuinely just such a joy to talk to you. Thank you very, very much.
Well, thank you, Lawrence. It's really been a pleasure to speak with you. It's been a lot of fun.
Thanks.
The Origins podcast is produced by Lawrence Krauss, Nancy Dahl, John and Don Edwards, Gus and Luke Holwerda, and Rob Zepps. Audio by Thomas Amison. Web design by Redmond Media Lab. Animation by Tomahawk Visual Effects, and music by Rickolas. To see the full video of this podcast, as well as other bonus content, visit us at patreon.com/originspodcast.